Hello everyone. In this lab, we are going to design a reactor. This lab is for the reactor design. Reactor design. So the problem is, uh, you have benzene that is C6H6, or we can say directly benzene. So benzene is react with the propylene to give cumene. Okay, cumene. So benzene is C6, C3. React with this C9. So, and cumene also react with the propylene to give diisopropylbenzene. Diisopropylbenzene, which is C12. Okay, so we have actually this is the main reaction, this one, and this one is the side reaction. So we want cumene to be more and side reaction to be less. So we have to design such a way that our uh, all the constraint will be met, and without violating the constraints, we have selectivity of cumene should be high, and on the same time we want reactor to be less size. So we want less TAC, uh, and constraint should not be violated. So this is the problem of this exercise or today exercise. Now, first of all, I will explain how to converge the reactor and the Aspen Plus, and then I will explain one by one what are the degree of freedoms of to design a flow sheet to design this reactor, and what are the constraints, and what are the what are the degree of freedom that are available for me and what are not available for me. So let's go for the firstly for the simulation part. So I will in today's exercise I will not do whole simulation. I have already done the simulation, so I will explain what to do only. Okay. So we have first we have to put the components. So now we have cumene, benzene, diisopropylbenzene, propene, and propane. Since if you see the problem statement, in the problem statement, propylene is not pure. So propylene has some 5% of propane in the stream. So that's why we have put the propane here or include the propane here. So these are the components. You have to put in the components, and after the component, the method we are using is Peng-Robinson method. After Peng-Robinson method, just run the simulation. After run the simulation, you will go to the simulation environment. In simulation environment, this is the flow sheet you are going to be convert today. So what are the parameters you need to convert this flow sheet? First, you need to know the what is the benzene fed to the reactor. For benzene, the inlet temperature is 41.25 degrees centigrade, because the flow sheet I am going to tell is only the half part of the or the first part of the total flow sheet, that is cumene process. So I am just explaining the reactor design. So that's why the fresh benzene, which is 100 kilomole per hour, has some recycled benzene with it, and fresh plus recycled benzene is fed to the reactor. So right now I am using only the total benzene that is going to the reactor. So this total benzene, the total flow rate is 140 kilomole per hour, and here there is some cumene in it, and mostly is benzene. So 99.9% benzene, and there are some cumene 0.001. So this is the mole fraction of this feed stream, and this is the pressure, and this is the temperature. And for propylene, we are going to fed 105.26 kilomole per hour of propylene, in which the in Inlet pressure of the gas is 1000 kilopascal and temperature is 25 degrees centigrade, and mole fraction 95% is propylene and 5% is propane. After that, we have to compress this propylene because the reaction is occurring at 25 bar. Since reaction is occurring at 25 bar, so we have to compress accordingly because we have vaporizer, feed effluent heat exchanger and heater, and all these unit operation has some pressure drop. So according to this pressure drop, we have to compress this gas to higher pressure so that we have pressure in PFR is approximately 25 bar or 20.5 24.5 bar. So for that, I have increased the pressure of 1760 kilopascal here in the compressor, and then the mixture of benzene and propylene is fed to the vaporizer. So what vaporizer does, in the vaporizer, whatever benzene we have it is in liquid form, but and propylene is in vapor form. So since the reaction is in the vapor form, so we want benzene to be vaporized. So the mixture is fed to the vaporizer. So in vaporizer, we put two spec such that pressure we have given minus 100 kilopascal. So minus 100 kilopascal means we are giving the pressure drop. So whatever the pressure at the inlet, so outer pressure drop is 100 less than the inlet pressure. So minus 100 means the pressure drop delta P, and the work of this vaporizer is to vaporize all the feed. So that's why we have taken the vapor fraction of 1 instead of giving the temperature, because as when we are going to optimize the flow sheet using the MATLAB, so we have a degree of freedom of this total C6 what is coming to the reactor. So this is going to be changed since this is more. So our our dew point temperature will be changed. So that's sorry, bubble point temperature will be changed. So uh, that's the reason we don't know what temperature we have to kept. That's why we have kept the vapor fraction to be 1, and then valid pressure will be the vapor. Instead of vapor liquid, we have to put the vapor only. Okay. Instead of vapor only, we should have to get vapor liquid because there is some problem here. If we give the vapor only, so we will took the because at inlet we have liquid now. There is some liquid, so we can't have very fit of liquid only, vapor only. So it should be vapor liquid because inlet is mixture of vapor and liquid, and outlet is total vapor. Okay. Now, if you see the flow sheet in the problem statement, you have the feed effluent heat exchanger where you are heated this vapor uh, uh, from the reactor outlet stream. Since the reaction is not happening, we don't have this stream, reactor outlet stream. So, before putting this FEHE, we fed the vapor to the heater first. First, the total vapor is fed to the heater, and we put the temperature to the heater to be the 300 degrees centigrade and pressure to be the minus 100 kilopascal, and then we will do the reaction in the PFR. When we have this stream, this PFR outlet stream, then after that we will put the FEHE where we can heat exchange using this hot stream to cold stream. And for the input part, we put the cold steam outlet temperature to be 280 degrees centigrade and the minimum temperature approach to be 10 degrees centigrade in the heat exchanger. So this is the heat exchanger, whereas this is the heater. So for heat exchanger, you have to go to exchanger, and here we have heat exchanger, and you can have heat exchanger like this and like this also. So you can choose this, and then after choosing this, when you go to the material stream, you will have this one is hot required and this one is hot required output. This one is cold required input and this one is cold required output. So if you just rotate it, uh, then you have, if you rotate it like this, then you have this one is cold required, this one is cold required output, this one is hot required, and this one is hot required output. So using R, I have rotated it, and then you have to flip vertical. Then you will get this type of symbol: cold, cold, hot, hot. Okay. Now after heater, you have to run the reaction in the packed bag reactor. In packed bag reactor, what are the inlets? Inlets are reactor with a constant thermal fluid temperature, because the reaction is the exothermic reaction. Since the reaction is exothermic reaction, your uh, temperature in the reactor will increase, but there is a limitation of temperature. You cannot go beyond the 400 degrees centigrade of temperature in the reactor. So that's why we have a coolant. We have a coolant there in the reactor. So for that reactor with we have to choose the reactor with type. This is reactor with a constant thermal fluid temperature. With the total fluid thermal fluid total heat transfer coefficient is 65. It is written in the problem statement. But this 65 is initial guess. We have to calculate it using the Bolter equation. I will explain later. And after once this flow sheet is converged, then I will explain what are the degree of freedom and what are the constraint uh, we have to maintain. Okay. Now put this as 65 and the thermal fluid temperature with 346 degrees centigrade. After that, you will go to the configuration part. In configuration part, we have a multi-tube reactor. In multi-tube reactor, we put the number of tubes to be 1950, or we have given in the problem statement what is the value. In the problem statement, the number of tubes I have not given, so we will give. So in the problem statement, if number of tubes, let's say it is 1500, so we will give the 1500, and your diameter is 3 centimeter, and we will give the initial length to be the 5.9 meter, and then run the react then and then not run the reaction, but you have this. After this, you will go to the pressure. Here pressure, as for the initial guess, you have to give the 100 kilopascal here first, because in the problem statement it's written that pressure drop in each unit operation is 100 kilopascal. So for initially, you will give the 100 kilopascal here, and then you will see you don't have a run option because you did not define the reaction. So then you have to go to the reaction here. Here we have I have given two reaction, but you have to just given the one reaction because this is the whole Cumene flow sheet. I have deleted the separation part and the task alkylator reactor, but I forgot to delete the reaction also. So you have to just put the one reaction only. So this is reaction one. When you go to the reaction uh, here and you do the new, in new you will get R1. So in R1 you have to choose type as a power law, and then when you choose power law you will get here. So here when you do new, in new what you have to do, reaction type you have to select is kinetic, and after kinetic what is the reaction I have just explained earlier, that is benzene and propylene to give cumene. So sorry, so benzene is a reactant and propylene is a reactant. So for benzene and propylene, we have coefficient of -1 and -1 because these are the reactant. And if you see in the problem statement of the kinetics part, since this is the kinetics, you can see rate expression. The order of the reaction with respect to benzene and with respect to propylene is 1. So that's why the exponent here is 1 and 1. And cumene is your product, so coefficient is 1. And the another reaction is your cumene is further alkylate to DIPV. So we have cumene and propylene as a reactant with a coefficient of -1 and exponent of 1 1. You can see here CC and CP. The order of reaction with respect to cumene and propylene is 1 only. That's the exponent is 1. And your product is DIPV. This is that is diisopropyl benzene. So coefficient is 1 here. Now you define the reaction, but after defining the reaction, you have to give the kinetics also. So since for kinetics, let's say I have selected the first reaction. For the first reaction, this is benzene plus propylene gives cumene. Since the reaction is in vapor phase, so reacting phase is vapor, and rate basis is your reactor volume, because all the unit are given in the kilomole per meter cube. It means uh, we are working on the basis of the volume of the reactor, not the uh, catalyst rate. So that's how we have given the rate versus the reactor volume or reaction volume, and reactive phase is vapor. So in the first phase, in the first for the first reaction, we have used the power law kinetics. Since it is the power law kinetics, so K is equal to K naught e की power minus E by RT. So here it is n is like this T by T naught की power n. So n is 0 here because we are not using any what to say that collision theory or that other theory mechanism. We are just using the Arrhenius equation. So n is 0 here. So then comes to be the RNA factor, that is K naught, and activation energy. From RNA factor and activation energy, it is given here in the problem statement. This is 2.8 10 to the power 7, and this is your activation energy for the first reaction. So write the value of activation energy and the uh, K naught. So K naught unit is here in SI unit, and we have given the value in SI unit, so you don't have to change the units. Just put the values. And for the second reaction, reacting phase again vapor phase, rate basis again reactor volume, and just put the value of K naught and activation energy from the problem statement. When you define the reaction, you will go to the reactor and go to the reaction and select the reaction you have just defined. After this, you will run the simulation. As soon as you run the simulation, you have at the outputs and values. Since you have defined the uh, length to be 5.9 meter and number to be 1500, so you will not get the conversion of 99.5%, whereas I have got the conversion of 99.5% because I have also uh, uh, here I have also define the design spec. So you don't design you don't till now you don't design you don't define a design spec. So you don't have a 99.5% of conversion, but still you have some conversion. And if your system is running, that means your data is correct. Okay. Then after the reaction, you have the PFR outlet stream. In PFR outlet stream, if you see, the temperature is approximately you have the temperature of whatever the reactor coolant temperature you have given. This is 346 degrees centigrade if you have given. So your temperature is approximately 346 degrees centigrade. Okay. And if you see the temperature profile of the reactor with the reactor length, you can see the temperature profile should be look like this. Actually, you have given the 5 meter of length, so your profile should be up to here only. Okay, not till 28 meter, up to here only. So your profile is like it has a maximum of 410 degrees centigrade. Okay, now what you have to done after getting this PFR out, you will just now include the FEHE. And in FEHE, the hot is this PFR out, and the cold is your vapor inlet. And then this is your cold outlet. Then this is your hot outlet. Okay, and in the FEHE, you have to define a cold stream outlet temperature to be 280 degrees centigrade and minimum temperature approach to be 10 degrees centigrade. Okay, and then this hot outlet is sent to the cooler, where in cooler you will give a pressure of minus 100 kilopascal, which is means a pressure drop of 100 kilopascal and temperature of 170 degrees centigrade. We want to uh, cool the cool or cool the stream. So we want actually liquid at the output. Since we have this, and then you have then after that you want to put a drum or not, don't want to drum, that is not the part. Actually, the in today's exercise or in this exercise, this is not required. Cooler, drum, and valve for. So if you don't want to put, no need to put. Okay, this is up to here. It is completed. So now you have just completed one part, that is whatever the initial guesses or initial values you have provided with the in the problem statement. You have just converted the reactor. Now you have to design the reactor. So if you are going to design a reactor, let's say what are the constraints we have and what are the uh, parameters we have. So in reactor, what are the parameters we have? We have total benzene fed to the reactor, total benzene flow rate fed to reactor. This is the first. Second, we have inlet temperature of the reactor, inlet temperature of the reactor. Third, we have coolant temperature also, coolant temperature. Then we have heat transfer coefficient. What is the value of heat transfer coefficient? Why it is 65 only? Heat transfer coefficient. Then we have length of the reactor. Actually, diameter of the reactor I am not taking as a variable, because diameter came with some there is a standard size of the diameter. So we have taken the 3 centimeter of diameter. So diameter is not going to change. So we are going to change the length of the reactor only. So now, so we have length of the reactor. Then we have number of tubes. Number of tubes. Then we have pressure drop across the reactor. Pressure drop across the reactor. For initial gas, we have given the 100 kilopascal, but uh, we have to check this pressure drop. It is 100 or it is less. Okay, and what we have. Okay, now this is the variable we have. Hmm. Hmm. These are the variable we have. Now, what are the constraints? So here I can put it as a degree of freedoms, DOFs. So these are the DOFs. Okay. Now we have to define the constraints. So what are the constraints? We have constraints. First constraint is maximum temperature in the reactor cannot exceed 400 degrees centigrade. So T max should be less than or equal to 400 degrees centigrade. If you cannot go beyond in the reactor, in the reactor. Since this is an exothermic reaction, so we cannot go beyond the 400 degrees centigrade. Second, we want conversion of bracket my x will be 99.5%. So these are the two. And third is we want high heat transfer coefficient. So for high heat transfer coefficient, we want high Reynolds number. So Reynolds number will be greater than or equal to 10 to the power 4. Since we have high Reynolds number, so from the Reynolds number we can calculate the this rho Vd by mu is equal to Reynolds number, and if we take the 10 to the power 4, we can calculate the superficial velocity, that is Vs. So we can calculate Vs here. So Vs and density and mu will be this is d is diameter, rho is density, and mu is kinematic viscosity, dynamic viscosity. So these para dynamic viscosity and density you can take it from the Aspen plus, and diameter of the reactor is your 3 centimeter. So if you calculate the Vs come out to be, I think I have to see the value. What is the Vs? 0.13. So Vs come out to be 0.13. So it means Vs should be greater than 0.13. So superficial velocity is greater than 0.13. So from the Reynolds number, we get the superficial velocity, which is greater than 0.13. This is your next constraint. So we have these three constraints, and one more constraint is fourth one is your selectivity. So selectivity, let's say it should be greater than 0.98 or 98%. Okay. So these are the four constraints we have. Now for these four constraints, what variable can be fixed? So since diameter is fixed, so we can fix length of the reactor for conversion x is equal to 99.5%. So 1 degree of freedom, that is length, is fixed for the conversion. Okay. So now put this as a design spec in the Aspen Plus. So go to the Aspen Plus. In Aspen Plus, you have a flow sheeting options. In flow sheeting option, you have a design spec. In design spec, you select new. In new, you will get DS1. In DS1, you will have you have to define the variables spec and vary. So here I want to define the uh, conversion. So what is the conversion means? Conversion is your, so x is, let's say conversion in terms of propylene, because propylene is your limiting reaction. So we have propylene in minus propylene out divided by propylene in. This is the conversion. So I have to define this equation in the design spec. So for that I have defined the input propylene and output propylene. Since input propylene is your PFR in stream name, and output propylene is PFR out stream name. So in PFR in, I have defined the component propylene, and in PFR out I have defined the propene also. So in defined, we have defined the two variable P in, P out, and both are mole flow. And then this is the spec, that is this is the equation of conversion, which is P in minus P out divided by P in, and the target value is 99.5%, so 995, and tolerance is 0.0001. So for this target value, I have what I can vary. I can vary the length of the reactor. So length of the reactor is your variable is your block variable. So you choose the block variable, then block PFR, then variable length, and unit is meter, and give the upper and lower bound 1 on 250. So right now, if you go to the result part, and I have done for the 96% conversion, my length of the reactor is 27.65 meter. If I run it again, this is come to be 26.19 meter because I have just decreased the conversion. Okay, so this is how you can design. You can define the design spec. Now, length of the reactor is used for the conversion, and uh, after using the length of the reactor, uh, we have to find out in if you see here, na, you have if you see we have to find out the heat transfer coefficient and pressure drop across the reactor. We have to find, and then number of tubes. So how to find the heat transfer coefficient? So heat transfer coefficient, we have the equation, Dittus-Boelter equation, Dittus-Boelter equation, which is equal to Nusselt number is equal to 0.023, Reynolds की power 0.8 and Prandtl की power 0.3 or 1 by 3 also we can take. Okay, let's say 1 by 3. I think in the problem statement I have showed the 1 by 3. Okay, 1 by 3. So Nusselt number is nothing but HD by K 0.023. Reynolds number is let's say 10 की power 4. So 10 की power 3.2 and Prandtl number is mu Cp by K की power 1 by 3. So mu Cpk and this diameter of the your tubes or PFR, which is 3 centimeter. So all these things you know. So H is only unknown. If you find out the H from this equation, you will get H to be 62 kilowatt per meter square. Oh, okay, not 62 kilowatt. I think this should be 63 watt. Huh? 62 watt, not kilowatt. Watt per meter square Kelvin. You will find out this. So this value you have to use in your simulation. You have to find the value from this equation, and how will you get this viscosities and heat capacities. So for that, what you have to do, you have to go to the PFR steam results, and steam results you already have the molar mass density kg per meter cube, input and output mass densities. So you will take the actually the average of these two. Take the both of these and just divide by two. So average value of this mass density. So you have mass density, then you want viscosity and heat capacity. So viscosity, heat capacity is this value, joule per kilomole per Kelvin, and for viscosity, I have thermal conductivity also, and I have heat capacity also, and I have viscosity also. So all these things in this unit you have to take, and in your simulation you will not have these values. So how to add this value? You have to go to the add properties. In add properties, you just search viscosity. You just search viscosity, then you have the in my simulation I have already added the dynamic viscosity, so that's why and here you have the viscosity of the mixture, MUMX. You can take this As a viscosity, then we have, I think, thermal conductivity. So check for thermal conductivity. Now you have the thermal conductivity of the mixture, Kmx. And then you, if you want any properties, you can add from the add properties. Okay, all the variable you will easily available. Now you have calculated this h, and you have already calculated the this superficial velocity. From the superficial velocity, you have to calculate the pressure drop across the reactor. So pressure drop across the reactor is calculated using the Argon equation. So Argon equation is delta P by L is equal to 150 mu Vs 1 minus epsilon whole square divided by phi square dp square epsilon cube, and plus this is from the Stokes theorem, or uh, uh, they are 2% now. Kozhnik-Kármán equation, and this is from the bulky polymer equation, 1.75 rho Vs square 1 minus epsilon divided by phi dp epsilon cube. So this is for the in the range of high Reynolds number, and this is for the in the range of laminar flow. So from these two equation, Argon equation is made. So this is the Argon equation. So in this equation, you know the mu, Vs, epsilon, phi is zero point 0.9 as given in the problem statement. Particle diameter is 3 mm and epsilon is zero point 0.5. So all the values you know, even density you also know from the Aspen Plus. So all the data you know. So you find the delta P by L, since L is changing, you because you are changing the variables. So your pressure drop across the reactor will change, and whatever pressure drop you will get from this equation, this pressure drop is applied in the uh, Aspen Plus. Okay. So now we have calculated the pressure drop from Argon equation. So pressure drop is completed, and length of the reactor is used for the conversion. Now number of tubes. So how you will get the number of tubes? So Vs is we are getting the Vs value of 0.13, which is for the Reynolds number of 10 to the power 4. But what is the superficial velocity in our simulation? We don't know. So we have to find this superficial velocity. So superficial velocity is nothing but Vs is equal to Q by area of the reactor, Q by A. So Vs is equal to Q is known, that is volumetric flow rate. So if you go in the Aspen Plus, you have the volumetric flow rate, volume flow cubic meter per second. This is given in the Aspen Plus. So you will take the average value of this volumetric flow. After you have volumetric flow, what is the area? So this area is the cross section area. So for cross section area, we have the catalyst loaded also. So since catalysts are loaded, we have a epsilon value of zero point 0.5. So total effective area is uh, epsilon, sorry, epsilon multiplied by pi d square by 4 multiplied by number of tube. Okay. So from number of tubes, whatever number of tubes here we have, we will calculate the Vs, and then we check this Vs is greater than or equal to 0.13 or not. If it is not equal to 0.13, then we will change the number of tubes. So number of tubes is calculated. So N tubes is calculated to fix the Vs should be greater than or equal to 0.13 meter per second. Okay. So number of tubes are used for this, and number and pressure we have calculated. So we and so number of tubes used for the Vs, length of the reactor used for the conversion, pressure is calculated from the Argon equation, heat transfer coefficient is calculated from the Dittus-Boelter equation. So now we have left with the three parameter, that is coolant temperature, inlet temperature, and total benzene fed to the reactor. So I am fixing one thing, which is inlet temperature. Inlet temperature to the reactor is 300 degrees centigrade. So we are not going to change the inlet temperature. So which it is fixed to 300 degrees centigrade. Now we have only two variable, that is total benzene fed to the reactor and coolant temperature. And we have two constraints also. One constraint is your Tmax and other constraint is the selectivity. So for the Tmax, coolant temperature is fixed. So T cool is fixed to make Tmax less than equal to 4, even less than equal to 400 degrees centigrade, and your total benzene flow rate F benzene flow rate is fixed to have selectivity of greater than equal to 98%. So all the variables are fixed. So now what is the now I will show you the algorithm how to make this algorithm. So algorithm is like, let's say we have select the number of tubes, any value. So and we choose NT. We have found Vs from the equation of Q by A. Then we compare Vs from Vs required. If this value if it is true, then we will go to the next step. Otherwise, we will change NT. Okay. After this, what we will choose next is your, let's say coolant temperature. So we will choose coolant temperature, choose any value of T cool, and then calculate this NT and this Vs at this T cool, and then after Vs we yeah, here we see we find the Tmax. We find the Tmax, and after Tmax we compare this Tmax with the Tmax required, and it should be less than 400 degrees centigrade. If it is true, then we go to next step. Otherwise, we will change the coolant temperature. Then again, the upper loop is choose F total, that is the total benzene flow rate, F total benzene, and here we will get the selectivity value. We will calculate the selectivity, and this selectivity is, let's say this is S. This S is compare with S required, and if it is true, then it is okay. If it is not true, let's say no, 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 here yes, yes, and yes, here yes. So we have at the end we have final value of number of tubes, F total and T two. So this is your algorithm look like. Uh, okay, this is your algorithm. This is the way you have to design the reactor. Now I will explain this thing in the MATLAB. How do you actually link your Aspen Plus to the MATLAB and how you will get the data. So for getting the data from the Aspen Plus, you have to go to the customize. In customize, you have a variable explorer. So in go to the variable explorer, go to the root, go to the data, and go to the block or stream, whatever data you need from the block or stream, you go there and you can select data from stream or block. I will explain for any of the variable. I will explain one or two times when we go to the MATLAB. So go to the MATLAB, and in the MATLAB we have lot of functions here because there are three loops. So all three loops I have made two functions. For each they have made two functions. So we have actually a total six functions, and there is one main file which actually uh, calculate, or which actually, what to say, run. So I will save this file first. Okay. Now, this is the main command to actually uh, connect your Spin Plus to the MATLAB. So Spin is your any variable name. So whatever the command is actx server and then apwn.document.40.0. So dot 40.0 is based on the latest version, that is the Spin 14. If you have the older version, which is you don't have, so forget about that. So for Spin 14, you have to use apwn.document.40.0. So this is the command to actually link the Spin Plus from the MATLAB, and this Spin is your variable. Now whatever you have linked the Spin Plus, this linking is done using the variable name Spin. Okay. This stat and mesh is nothing but you have given the file attribution, that is the directory you have given, in which directory you are working in. So this will save the directory in mesh. Now I have to give the file name. Which file name, actually which file you want to connect with MATLAB. So spin is your that variable where you have make a function or server to connect the spin plus files. So spin dot invoke is your, you are invoking that file. So init from archive 2 is a command, and mesh dot name is your actually the file path which directory you are working in, and in this file path your file name. So my file name in here is reactor design underscore cumene dot apw. So instead of apw file, I will connect the bkp file, because in for connection bkp file is best than the apw file. So you will connect with the bkp file. So we have names same name, but the extension is .bkp. So from these three commands, we have actually connect the Aspen file. Now, what does Aspen.visual do? Visual, if it is 0, it means whenever you run the Aspen file, it will not open. If it is 1, it will open. If it is 0, it will not open. Okay, so actually, when we do the optimization part, we have to do the iteration again and again. So if there are lot of iteration, your lot of files will be opening. And since we have less number of what we say license, so we don't afford to open too many files. Otherwise, your fmin count will fail because of the server issue. So that's why we will not open each time the files. So Aspen.visual is 0, and then Aspen suppress docs dialog logs is 1. It is like you are suppressing the dialogues. If let's say I don't have a direct answer for this. There are too much of files are opening for the Aspen Plus now. So you want to suppress dialogues. You don't want uh, each file has lot of other files opening in it. So that's this command do, and then aspen.indent.run to it is the command is for the running the aspen file. So you are running the aspen file from the MATLAB itself. From this command you are running the aspen file aspen.indent.run to. Okay. Now you have three variable. All other variable you have calculated using data folder equation or using your Argon equations. So only three variable we here, and in these three variable, the loop is look like this. So the outer loop is total benzene, then inner loop is T equivalent and T. So on the same way, I have defined this variable. So let's say the variable name is total flow, that is TF. So we want the initial value of TF. So the initial value of TF I have taken from the spin plus itself, whatever the value we have converged for initially. So how we take this value? So let's say uh, we want the TF. And so how we will take this value? So you will go to the variable explorer. In variable explorer, we know total C6 is your stream name. So we will go for stream. In stream, we will go total C6. In total C6, we will go for output because uh, this is output total flow. So in output, we will go for the total flow if we have this variable. We have total flow. So we have total flow which is 140. So we will just copy here call function call this is the stream name or variable name. So from this variable name you can call this variable. So you will copy this application.tree.find node. And in MATLAB, what you have to do, just copy this application tree find node data stream total CSS output total flow, and this you will copy. And in this, what you have to do, you have to just put Aspen dot before and dot value after. Dot value means you will giving the value of this stream, and Aspen dot means you have connected this file from the Aspen uh, function Aspen variable. So from Aspen variable you are so it means this Aspen means you are going in this file. In this file you are getting this variable, and in this variable you are taking this value, and this value is coming to the TF. Since this is value na value value, so that's why we have given the dot value there. Since it is not a case sensitive, so we can have small and capital also. And keep in mind, in MATLAB we have to use only single quotation, not double quotation marks. Similarly, in T in cool, the same way you will define the T in cool. So T in cool is PFR. It is the PFR output. So you will go in PFR output. It is coming in the B temperature mixed, and I have taken the 51 value. Actually, it is not 51. Actually, it is the last one. So whatever you have the last value, you will take that value. And one more thing, in Aspen Plus, I have made this graph now, this temperature graph. My graph is very smooth, and there are lot of points there. So how you will get these lot of points? To get these lot of points in your Aspen Plus, you have to go to the report options. In report option, you can have two things. You can uniformly spaced profile, or you can have multiple section with uniformly spaced profile points with each section. So I have defined multiple sections. So in this section, I have defined a total of 5 sections. So each sections I have 20% of total length, and in the initial section I have defined a 20 number of variables intervals, and all other section I have defined only 10. So I have total 60 variables. So if I take in the variable explorer, if I go to the block TFR block TFR, and here output, in output it will take some time to open because there are a lot of output. If you go in btemp, in btemp mixed, I have 61, I think 61. So this is your last stage. Next stage your section. So last section value I have to take. I have taken 51 because in previously I have given 51 only. But if you see in the temperature plot, here it is constant only. So you can take any value. It is also a initial guess only. No. So this value we have take. Then number of tubes same. Output number of tubes you have taken, and then what happened? I have make one loop, one bigger loop. If this bigger loop is converged, all other are converged. So this is flag one, count 1 0, then while flag. So first is the most inner loop. In the most inner loop, I have to calculate the number of tube while keeping the superficial velocity to be 0.13. So we have calculated the V naught and number of tube from this function calc nt1 nt. So I will go to the calc nt1. In calc nt1, I have defined the function for a Newton-Raphson method. I have used the Newton-Raphson method to calculate the number of tube. Since number of tubes cannot be real, it should be integer value. So you can increase only by one or decrease only by one. So it may happen uh, you the value of 0.13 you will get for for value of let's say zero point 0.6, let's say you will get a value of 1500.6 number of tubes. This cannot be happen. So you will get 1501 instead of 1500.1.6. So you will never convert that value of 0.13. So for that, I have defined it using this maximum of 2 round 2, and here I have taken this ni plus, instead of sending directly the nt, I have sent the ni, and then I have do it for the uh, integer. So whatever the value and number two I have got, I have to take the number of two just next tenth. Let's say if I got the 65, then 70 I have to take. If it is 72, then I have to take 80. So seal is the next tenth. Next, मतलब seal means uh, higher value, approach toward infinity. So from the seal and floor seal command, I have taken the next highest value of the number of two, which is divisible by 10. So in this here, I have also called a function calc v naught. So in this function, I actually calculated the this v naught value. So this is the v naught value. I have already global the Aspen because Aspen is the main variable here. So I have globalized this variable. So since this is global, I can use it directly use this that Aspen variable. So from the Aspen variable, what first I have done, I have first put the number of tube value, whatever the number of tube I have defined or choose initial value, I have given to the input to the PFR. So here, if you want to give input to the PFR, this is the syntax. So Aspen.application.tree.find node. So instead of output, we go to input and find the variable in the custom variable explorer. Here, this is the variable explorer. From the here, you have to find that variable. So this should be, if you are given the input, it should be input. In input, I think it should be a number of tube. There should be a variable number of tube and tube. So this is the n tube, and this is the call of that variable. So call and dot value, and I have given the value to be nt. Then I have run the simulation. After running the simulation, I have find the I have take the data from the spin, that is the volumetric flow rate inlet and outlet, and then take the average, and we know the porosity to be the zero point 0.5, and diameter of the reactor is 3 centimeter, which is constant. I have already take from the Aspen Plus. If I want to take, I want to change. So this is general. Then VSS calculator using uh, QF divided by E number epsilon into number of tube into pi d square by 4. So here I have used a double and double. For V naught total I have used double, and for NT I also used double, because the problem here is NT is your integer type. So when you give the NT in the spin, na, this NT is integer type. Since this NT is integer type, so this V naught will become integer type. Since V naught is not integer, V naught is real, 0.13, we have to take the value. So since V naught is not integer, so we have to use the double. We have to convert this integer to double. That's why we have used the double here. Otherwise, you will always get a zero value for V naught. So this is the first function. Then you will get the number of tubes. Converge number of tubes to get the V naught value of 0.13. Then what you have to do? Then you have to calculate the pressure drop. So for pressure drop, I have calculated the density. Uh, take the value of L, take the value of input and output densities from the Aspen Plus, and then the particle diameter is 3 mm. It is given epsilon is 0.5. Then you have to take the dynamic viscosity from the Aspen Plus. Then the specificity is zero point 0.9. Then calculate the Kuzhny-Karman delta P and bulky polymer delta P. And then this delta P I want in kilopascal. So since for kilopascal it is divided by 10 to the power 3 and multiplied by L. So we will get the delta P across the reactor, and this delta P is used in the reactor, and number of tubes, whatever the number of tubes we have get, that number of tubes we have to use in the reactor. So change delta P and number of tube and then run it again. Okay, this is the first loop completed. Then after completing the first loop, we have to go for the second loop. That is the coolant temperature. So we again call the second function, that is the calTin. In calTin, we have passed the value of T in cool, that is the initial value, and that passed value again we have calculated the Tmax from that, and it is compared with the Tmax required, and then again we have used that Newton-Raphson method, Newton-Raphson method, and Newton-Raphson method. We have calculated the T in cool. Here we have also for Tmax we have also calling a function cal Tmax. So in cal Tmax, what we have to do? We have to first give the coolant flow rate, sorry, coolant temperature value. This is the function file. This is a variable name we have to take in from the Aspen Plus, and this input we have given T in, and then run the system, and then directly we will take the Tmax value. Okay. Then again, when we get this value, we will give this value to the Aspen Plus cool T and run it again, and then we find the total flow rate according to selectivity. So we will pass the total flow rate, and here we have the selectivity, and this selectivity is calculated using this function. We have to give the Cumene input, Cumene output, and DIPB output, and then your selectivity is Cumene output minus Cumene input divided by Cumene output minus Cumene input plus DIPB output. So total Cumene output minus Cumene input and total DIPB output divide कर दो, यहाँ selectivity आ जाएगी. This is come out to be 0.97. This is not in 100. So we will multiply by 100. So we will get the 100. We have multiplied by 100. Na? This is our required selectivity. So now all three are done. Then we will check the selectivity we are getting here and the selectivity we are getting before, not selectivity, whatever the value of f dot we are getting now and the previous f dot value, if it is very less than this value and count is more than 1000, then we will stop the loop, and if not, then we will give the value we have just calculated. These value we will give to the Aspen Plus, and then again we will do the loop, and when this loop is converged, then we have this value. So let now we will I will close my Aspen file after saving it. Now I will run this simulation. Let's see what happens. So file is open. Now we have this value we are getting. Since in the first this value we have display empty, so this was empty is displaying. When it will converge, it will not display. So it is 777. Now in Tmax we have displayed Tn, so this is Tn is given. When it will converge, it will not display this. Not converge type now. Now it is converge. Now this is total flow rate. We have displayed this total flow rate. That's why this is displaying. So again, in the first loop, we have given the initial value of 140, and again we are getting 146 and some other value. So that's why the second loop is start. Again at number 2 it is calculating. It's taking too much time. Actually, something to it's not converging, but it will. So I will skip this part and my simulation is converged. So after converge, you can see I will get the number of 2040, T max of 399.99, delta P I am getting 46.81. So if you put these values in your CSTR and your F total coming out to be 148.88. Okay. So this is the way you have to perform all your calculation. And in previously, I have seen you the my calculation going to maximum because he there I have given this constraint. Na? In that constraint, I have given this instead of 3000, I given 2000. So you just put 3000 here. So then it will not be a problem. Okay. That's it from my side.